Swayam Prabha. Digital India. Educated India.
Welcome to today's lecture on basic control systems for mechanical engineers. Today we are going to study about state space. So let us start with an example. Let us take a simple spring mass damper system. So this is the mass M with coordinate y, to which we attach a spring with constant K and damper with damping ratio C. And let us say there is a force which is acting on this mass. Then the equation of motion for this system will be my double dot plus cy dot plus ky is equal to F. So m is the mass, c is the damping constant, k is the stiffness, y is the position of this mass, F is the force, and the dots denote the derivative. So a single dot denotes the first derivative, that is the velocity, and double dot denotes the acceleration. So let us put this equation of motion into state space form. So let us define two states. The first one is the position y, and the second one is the velocity. So here we are selecting two states because this equation is a second order differential equation. So we can if we substitute these values of x1 and x2 into our equation of motion, we get mx2 dot plus c x2 plus k x1 is equal to F. So based on this we can express x2 dot as minus c by m x2 minus k by m x1 plus F by m. So now we have this differential equation in terms of x2, x1 and the derivative of x2. So the state space representation comprises of basically two equations. The first one is the state equation and the second is the output equation. So the state equation is of the form that we take the derivative of the states. So that is x1 dot and x2 dot, that will be equal to some matrix times x1 x2 plus some vector or matrix. In this case we are going to consider, since we are considering only single input single output systems, it will be a vector times the input, that is in this case the force. So this equation we need to find these matrices, this matrix and this vector. So basically x1 dot will, from this particular equation, will be y dot, and from this equation we can definition we can see that y dot is equal to x2. So we will have 0 and 1, and since there is no force coming in, this part will be also 0. For the next equation what we are going to do is we get minus k by m times x1 from this equation plus minus c by m times x2 plus 1 by m into f. So, this is our state space equation in general form. So, this is x. So, this bar denotes that it is a vector. So, we are taking derivative of this state vector x. This matrix we denote it as A. The double bar denotes that it is a matrix. Then we have this x bar, that is state vector, and here we have B bar. Since it's just a vector, we are just considering single input single output systems, and this particular, let us say U, which is the control input. Now this is the state equation. So we had a second order differential equation which we have converted into, you can say, like into first order, two first order differential equations. Now we look at the output equation. So say output we desire is y, that is the position of the mass, then that will be equal to some vector times this state vector plus some constant times u, and u is, as we defined, is equal to f. So this particular vector, since the quantity we desire is y, that is x1, it will be 1 here, 0 here, and there will be no contribution of the force. So this is represents our output equation, and this matrix is denoted, this vector is denoted as C, and this is a constant T. So any state space equation is of the form x dot plus ax is equal to ax plus bu, and the output equation is cx plus du. The matrix A is called the state matrix. This vector matrix B is called the input matrix. C is basically the output matrix or output vector, and D is the feed through matrix or constant. The advantages of a state space representation. So why do we need to study the state space representation? So we are studying state space representation because it presents certain advantages. One, can be applied to nonlinear systems. Second, can be extended to multi input multi output systems. Third, can be applied to time or parameter varying systems. So the basic idea is it can be applied to nonlinear systems. So this A, B will then just be some vector of functions. It can be applied to multi-input, multi-output systems. So instead of U being just a vector, similarly Y being a vector, being just constants, they can be vectors. This can be also applied to time or parameter varying systems. So here what we are considering that A, B, C, D are constant, but they could be a function of time or some parameter, and then it can be applied to time or parameter varying systems. So these are the advantages of the state space representation. Another advantage we get is many controllers are more can be easily applied with the state space representation, and we will be discussing some at the end of this lecture. So, state space is just a form of representation of the system similar to what we have seen so far in the course about transfer functions. So, we can always convert from the state space to transfer functions, and to do that we have the formula like g of s, which is the transfer function, is equal to c times c into inverse of si minus a, where s is the Laplace variable and I is an identity matrix of the same dimension as a, which is basically equal to the number of states, times b plus t, and the stability of state space representation, or rather this system given in the state space representation, can be obtained by checking eigenvalues of A. So, basically eigenvalues of A are the poles of the system, because if you see this representation, that is this part Si minus A, this denotes the characteristic equation and is quite similar to the method we use for finding the eigenvalues. So, with that, now we focus on understanding how we can get the response, that is the output response from the state space representation. So, let us assume that the state at a given at time t is equal to 0 is equal to some x naught. So, this is our state space representation. So, for the solution, let us multiply this by e to the power negative at throughout, and once we do that, we can pull this part here. So, we get e to the power minus and this is equal to e to the power minus at p. So, if you see this particular expression, we can denote it as the derivative of this entire function. So, if we take the derivative of e to the power minus at into x t, we will get this particular function, and this we equate to e to the power minus at b. So, now we have this equation. So, we will integrate to get e to the power minus at x of t, and our integration limits go from t to 0. So, if we look at the value of 0, we will just get the initial state, and this will be equal to going from 0 to t e to the power minus a tau b u tau t tau. So then we can express this as x of t is equal to, so we will throughout multiply by e to the power positive at to get e to the power at times the initial state plus this integral. So when it's multiplied by e to the power at, we'll get a t minus tau b u tau t tau. So this basically represents the response of the system, and this part, if you see, this is the zero input response. So say our input u is 0, then this particular term here will vanish, that is the integral, and we are just left with e to the power at times the initial state. So this is the zero input response, and this particular part, the integral part, is the zero state response. So that means that if we assume the state to be 0, this part will vanish and we will be just left with this integral part, that is the contribution of the input. So now we will move to some important concepts which are used to understand the system and to design controllers. So first we will come to controllability. So an LTI system, that is the linear time invariant system, is controllable if for every state x star and every finite time t which is greater than 0, there exists u of t, so that t goes from 0 to this capital T, such that the system state goes from the initial state equal to 0 to some state x star within a finite time t. So the whole idea is we want to move from 0 to x star within a finite time t. So can we find the control input which makes this possible? If there exists a control input which makes this possible for all states x star and for all states t, then the corresponding LTI system is controllable. And the best way to determine whether this an LTI system is controllable or not is to make the formulate the controllability matrix, which is given by B AB A square A square B and so on till a to the power n minus 1 b. So this is the controllability matrix. If this matrix is full rank, then system is controllable. Okay, so just to summarize the concept of controllability, the understanding is for every state x star, if there is a, and for every finite time t, if there exists a control input which takes the state from 0 to x star, then it is controllable. So controllability is basically a property of the system, and the controllability matrix is given by this expression, and if this matrix is full rank, then the system is controllable. So let us consider a few examples. So let us consider we have this particular system. So if we write down the controllability matrix for this, what we get is 2, 1, minus 4, minus 1. So this will have, we'll consider only these two parts, B and AB, because n minus 1 is equal to 1 in this case. So we'll just have 2 columns. So if we consider this now controllability matrix, it's full rank, so it's controllable. Now let us consider another example. So this was our first example. Let us more or less take the same system but make just a few changes here. So we have minus 2, 0, 0, minus 1. The only thing we are going to change is here in the first example we had 2 and 1. Now we are going to put 2 and 0. Remaining everything remains the same. So now if we formulate the controllability matrix, we'll get 2, 0, minus 4, 0. So here if you see, this is not full rank, so not controllable. So why is this not controllable? So if we look at this state equation, we'll write down the corresponding differential equation. So you get minus 2x1 plus 2u, and x2 dot is equal to minus x2. So here if you see, what happens is the u is part of the first differential equation. So with change in u, x1 changes, but this x2 is totally independent of both x1 and u. So irrespective of whatever u we select, we cannot control this state x2, and that comes back to the definition that we cannot take it from any 0 to any vector x star. So we cannot control x2, we can just control x1, whereas in the previous case where it was controllable, it will be x1 dot is equal to minus 2 x1 plus 2u, and x2 dot is equal to minus x2 plus u. So here what you will see is that u can control both the x1 as well as x2. Now does it depend, okay, if this particular part is 0, 0, that's the reason that this system is uncontrollable? So here if we see in this example 2, you can see that u is not directly adding or making any contribution to the state differential equation for state 2. So is that the case that only when this term is 0 it becomes controllable or not controllable? So for that, let us look at another example. So what we are going to do, we are going to take this same system, but here instead of this 0 we are going to have a 1. So we are going to get 2, 1, minus 2, 0, 1, minus 1, 2, 0. So here, as you can see, u is not directly contributing anything to the differential equation for x2. So we will compute the controllability matrix, and based on that we get 2 0 4 minus 2, which is basically full rank. Sorry, this should be minus 4 2, and this is a full rank matrix, so it's controllable. So now we see that even though u is not contributing, it's still a controllable system. So for that we'll write down this differential equation again for this system, and what we see is we get this particular equation. So here what you can see is, although u is not directly contributing to the state x2, what you will see is that u contributes to x1 and x1 contributes to the differential equation for x2. So in this manner there is an indirect contribution from u and the system can be controlled. So next we will study a related concept, that is observability. So system, that is an LTI system, is observable if for any unknown initial state x, that is x at time t is equal to 0, there exists a finite time t greater than 0 such that knowledge of u and y, that is u of t and y of t over t going from 0 to capital T, is sufficient to uniquely determine that initial state. So the whole idea is, say you know the control input which you are giving, u of t, and say from some measurements you or some simulations you can get y of t over some finite time capital T. So if we have both these measurements over some time 0 to capital T, then, and if we can uniquely determine the initial state, then the system is observable. That is, we can basically observe the states given the input and output. So observability is how did we determine that if the system is observable or not. So it's a similar concept to the controllability. So we're going to write the observability matrix, so which is now C, CA all the way up to CA to the power n minus 1. If this is full rank, it means system is observable. So now let us consider an example for observability. So let us consider the system which we have seen earlier. So if we construct the observability matrix, we get 3 minus 6, 2 minus 2, which is full rank. So it's observable. You can consider another example, which is same system, instead of 2 we'll substitute 0. So in that case we'll get this is equal to 3 minus 6, 0, 0. So this is not full rank, not observable. So now once we have understood the concept of controllability and observability, we'll focus on now how we design controllers using this state space representation. So the most famous controller in basic one is the state feedback controller. So for the state feedback controller, the plant is given by this state space representation. So this is a single input, single output plant. We could also have multi input, multi output plants and still formulate a state feedback controller. And the controller here, I believe it's quite obvious from the name when we say state feedback. So it's U minus K times the state, where K is the gains of the controller, which as control designer we are going to formulate on how we are going to find that, and we are going to discuss that now. But basically it's U times minus Kx. So we are taking feedback from the states and multiplying big gains and formulating it to the control input. So say we want to represent this using a diagram. So this is U. As we see from the plant, U is multiplied by P for the state equation, whereas it's multiplied by the D for the output equation. So we have B and T. Now as a part of B, what will happen is, since it's B times U and it's added, so we're going to have some kind of a summer here, and the output of that summer is going to be the derivative of the states. The other input will be A multiplied by the states, and we know this derivative can help us get the states if we do integration. And the other part of the sum is, as I said, is A times X. So we can just do in this manner. And for the output equation, we already have D into U, we need C into X. So we are going to C into X, and that is going to be added to a summer, and based on this we get the output Y. Now this is the diagram which represents the plant. Now we are going to consider the controller. So the controller will take X and multiply it by K, and once we multiply it by minus K, we are going to feed this back into U. So this represents our state feedback controller plus the plant. So basically this entire part here represents the plant, and this portion here represents the controller. So now we have this controller equation, so let us substitute it back into the state equation for the plant. So what we'll get is derivative of x is equal to ax, and instead of u we'll substitute minus kx, so we'll get minus bkx. So this we can represent as a minus bk, the whole thing into x, and this represents the A matrix of the entire closed loop system, that is the plant plus the controller. And to find poles of this closed loop system, we find eigenvalues of this matrix ACL, which is equal to A minus B to K. So our job as controller designers is to find this gains K such that we can place our poles at any desired locations in the S plane. Okay, so we have now seen the state feedback controller. So let us do one example. So this is the state equation of our plant, and say we want to find if the system is stable or unstable. So what we are going to do is to get the characteristic equation, we have to find the determinant of Si minus A and set that to 0. So based on that we get S minus 1 into S minus 2 minus 1 is equal to 0. So we'll get S square minus 3S plus 1 is equal to 0. So as you can see from here, this system is basically unstable. And as a part of this exercise, what we are going to do, we are going to place poles at -5 and -6. So we are going to stabilize our system and place poles in such a manner that our performance criteria is satisfied. Now these performance criteria can come from different sources. So one we have seen, like it can come from time domain specifications, like we discussed earlier in our earlier lectures. So we are going to place poles at -5 and -6. So we are going to convert this unstable open loop system into a stable closed loop system. So our controller will be U is equal to minus into K1, K2 we have, and X bar, and our objective is to find K1 and K2 such that we can place poles at -5 and -6. So first what we are going to do is, as you can see here, we are going to take ACL, we are going to get A minus BK And from that we get 1 minus k1, 1 minus k2, 1 and 2. So now if we formulate the closed loop system, we will get s square plus k1 minus 3 into s plus k2 minus 2k1 plus. Now if we want to place our poles at minus 5 and minus 6, the desired characteristic equation will be of the form s plus 5 into s plus 6 is equal to 0. So that's basically s square plus 11s. So what we are going to try to do is we are going to try to match these two parts. So we are going to match this k1 minus 3 will be equal to 11 and this part k2 minus 2k1 plus 1 is equal to 30. So based on this we get k1 is equal to 14 and k2 is equal to 57. So these are our controller gains for the state feedback controller. Now this was now let us consider another example. We are going to consider this more or less the same system, only for the fact that we are going to, instead of 1 we are going to consider 0. So our second example we will have 1 0 1 2 and if we write down ACL, we are going to get 1 minus k1, 1 minus k2, 0, 2. So if we try to find the eigenvalues, what we will get is s minus 1 plus k1 into s minus 2. So as you can see here now, one of the roots will be at, you will get at one root will be always fixed at 2. So this system which we will be always unstable and we cannot place the both the poles at minus 5 and minus 6. Now why does this happen? This happens because this system is not controllable. So that is something as control designers we need to keep it in mind, that we can apply state feedback controller provided the plant to begin with is controllable. Because what you are trying to do, you are trying to use the control input u to place the poles at some desired locations, and that's only possible to place at any arbitrary location in the S plane if your system that is planned to begin with is controllable. So we have seen now that about the state feedback controller, and it can be only applied if the original plan to begin with is controllable. Another hindrance to applying the state feedback controller can be that you might not be able to measure all the states. So in such a scenario, we need to be able to estimate or observe basically states which we cannot measure, and that can happen provided those states are observable. So the concept of observability now comes into play, and we'll need, if they are observable, we'll need to design a state observer. So if the states are not measurable, then we can use an observer. So let us start. We have a plant. Now let us say we formulate an observer to estimate our states. So since we are estimating, we'll have the hat notation for the state. And for estimation, what we are going to do, we are going to use, as we discussed in the concept of observability, we use u and y. So we are going to also estimate y, and we are going to use the error which is multiplied by this gain L, which is similar to the gain matrix K for the state feedback. And this observed y is the C times the observed state plus du. Now this is the plant and this is the observer. When we combine them, what plays an important role is the error in this estimation, that is error between x hat and the actual x. So that error dynamics we can represent as x tilde derivative of x tilde is equal to, if we combine the two, that we subtract one equation from the other, what happens is the contribution of u will cancel and what we are going to be left with is equal to a minus lc times x, the state x hat, with difference between the x tilde, and x tilde is the difference between the observed state and the plant states. So now what we can do, what we are going to do is we want to control this error dynamics. A common method is to place the poles of this error dynamics based on our specifications, similar to what we have seen for the state feedback. So we'll place this L, we'll select the gains of this L, that is the components of this vector L, such that we can influence the eigen values and place them at particular locations in the S plane, and this can happen only if the system is observable. And the way to find L is similar to finding K in the state feedback. So now we have seen the plant, observer and error dynamics, and we are going to understand how to design this basically this vector L such that we can place poles of the error dynamics at arbitrary locations. The procedure is very similar to how we did for the state feedback, and let us for that look at an example. So let us take this plant as system. So the plant is represented by this state space equation, and we want to design a state observer such that eigenvalues are at s is equal to minus 1.8 plus or minus j 2.4. So as I said, the most important aspect while designing a state observer is to first check the observability matrix, and that comes out to be 0 1 1 0. So this is an observable plant. So we can formulate a state observer. So the error dynamics, as we have seen, is given by this equation. So if we want to place the eigenvalues of this error dynamics arbitrary at some locations, we need to find the characteristic equation, which looks something of this form. and we will consider L is equal to L1 L2. So, based on this we can get the equation to be S square plus L2S minus 20.6 plus L2 is equal to 0. Sorry, this is L1, and from the eigenvalues we can get the corresponding desired characteristic equation. So, that will be S plus 1.8 minus J. So, we are going to just multiply these two parts corresponding to these desired eigenvalues, and we will get S square plus 3.6 S plus 9 is equal to 0. So, if we compare these two equations, we will get L2 is equal to 3.6 and L1 is equal to 29.6. So, this is a state observer. If we substitute these gains, we will get our state observer and we can find the states. So, now we have studied and done an example about state observer. Now, as I mentioned, why we need to do this state observer is we might not be able to measure all states for the state feedback. So, we need to do this state observer to estimate those states. So, we need to understand how we are going to combine these two, because the reason for the state observer is the state feedback. So, if we want to do this both, combine both these two, the first step while designing the state feedback plus state observer is to first design a state feedback assuming that you can measure all the states. The next step is then we use the same control law and we design the observer based on what we have, based on the states. We design the observer, and then so the first step is to design the state feedback. Assuming all states can be measured. The second step is design the state observer for the system, and finally what we do is combine 1 and 2. So, this is how we can design a state of feedback plus the state observer, and that is all from understanding about state space representation in this course. And with that, I would like to conclude this lecture as well as the course. Thank you for all your time and attention.
Hello and welcome to this piece of literary snippet. We usually know William Shakespeare as the most revered figure in the history of English literature. But we often tend to forget that he has also been one of the most hated figures in literature. And here I am not talking only about those boys and girls who have to memorize long sections from Macbeth or King Lear or Julius Caesar before they can go and sit for their school or college exams. But I am also talking about people who are themselves quite famous authors. Tolstoy, for instance, considered the writings of Shakespeare to be, and I quote, crude, immoral, vulgar, and senseless. George Bernard Shaw absolutely loathed Shakespeare, as he did Homer. But perhaps no other criticism about Shakespeare is more damaging than the one which says that Shakespeare is a marvelous storyteller, provided someone has told him the story earlier. Now, this piece of criticism is particularly damaging because it is true. None of Shakespeare's plays contain any original story whatsoever. They are all written using pre-existing materials, pre-existing stories. Now, does that diminish the stature of Shakespeare as a dramatist? Well, I'll leave that for you to decide. See you in the next episode of Literary Snippets.